Google is one of those companies, and as the New York Times reports, Google recently said its machine can run software 13,000 times as fast as a traditional supercomputer.
We all know that digital computers changed virtually every aspect of our life. Well, the arrival of quantum computers could be even more historic than that. We're now in the initial stages of the next revolution.
At 3:47 a.m. on December 9, 2024, a chip no larger than a postage stamp was switched on in a secretive lab in Santa Barbara. And what happened next changed everything we thought we knew about computing, physics, and reality itself. For 4 minutes and 36 seconds, the quantum processor, codenamed Willow,
a quantum computer running on a special chip called Willow,
performed a calculation so complex that even the fastest supercomputer in existence would need longer than the lifespan of the universe to complete it. But the numbers were only part of the story. The engineers watching the monitors noticed something impossible: correlations and patterns in the qubits that defied every law of physics. Could a machine really be reaching beyond our universe? Was it possible that Willow was tapping into realities we have never imagined? The head of Google's quantum AI division suggested publicly that Willow may have tapped computational power from parallel universes. This isn't science fiction. This isn't theory. This is a door. Humanity opened, and no one knows what's waiting on the other side. Tonight, we're uncovering the full story of Willow, the experiment that shook the foundations of reality, and what it might mean for everything we thought was possible. What Willow actually is. To understand what Willow discovered, you first need to understand what Willow actually is, and why it represents a fundamental break from every computer that came before it. Classical computers, the ones powering your phone, your laptop, the servers behind everything you do online, operate using bits, ones and zeros, on and off. Every calculation, every image, every piece of information you've ever interacted with is ultimately reduced to these binary choices. Billions of tiny switches flipping back and forth, following logical rules that haven't fundamentally changed since the 1940s. Quantum computers are something else entirely. They use qubits, and qubits don't follow the same rules that govern ordinary matter. In the quantum realm, a qubit can exist as a 1, a 0, or both simultaneously. This isn't a metaphor. It's not a simplification for popular audiences. It's a measured, repeatable physical reality that has been verified in laboratories around the world for nearly a century. The phenomenon is called superposition, and it breaks every intuition you have about how objects should behave. When multiple qubits work together, something even stranger happens. They become entangled. The state of one qubit instantaneously influences another, regardless of the distance between them. Change one here, and the other responds there, with no signal traveling between them, no time delay, nothing connecting them in any way our physics can explain. Einstein called this spooky action at a distance. He meant it as a criticism.
The vast majority of sources on the internet claim that Einstein's spooky action at a distance referred to entanglement.
Proof that quantum mechanics must be incomplete. The universe, it turns out, wasn't listening to Einstein's objections. Willow contains 105 superconducting qubits, each one cooled to temperatures colder than outer space. The entire chip operates at just 10 millikelvin, a fraction of a degree above absolute zero, the coldest temperature physically possible. At this temperature, atoms nearly stop moving. Quantum effects become dominant. The ordinary laws of classical physics step aside. And that's when the real strangeness begins. The impossible problem they solved for decades, quantum computing faced a fundamental problem that seemed almost unsolvable. Error rates. Qubits are extraordinarily fragile. The slightest vibration, the faintest electromagnetic interference, even a stray cosmic ray passing through the laboratory can cause a qubit to decohere, to lose its quantum state and collapse into randomness. Classical computers handle errors through redundancy. You copy data, verify it, correct mistakes. But in the quantum world, you cannot simply copy a qubit. The very act of measuring it destroys the delicate superposition that makes it valuable in the first place. This is called the observer effect, and it has troubled physicists for a century. Early quantum processors were riddled with errors. Add more qubits and the errors compounded. Calculations became meaningless noise. The promise of quantum computing seemed perpetually out of reach, a theoretical possibility that could never become practical reality. And then Willow changed everything. Google's research team, led by Dr. Hartmut Neven, achieved something that had eluded the field for 3 decades. They made error rates decrease exponentially as they added more qubits. Read that again and understand what it means. In every previous quantum system ever built, adding more qubits meant more errors, more chaos, more noise drowning out the signal. Willow inverted this relationship entirely. The chip uses what's called a surface code architecture.
And we even got up close and personal with Google's dilution fridge, one of the coldest places in the universe.
A method of arranging qubits in a 2-dimensional grid where each qubit helps monitor and correct its neighbors. When scaled properly, this creates a cascading effect. The system becomes better at fixing itself the larger it grows. Dr. Neven described the achievement in terms that sound almost spiritual. "We have crossed below threshold," he stated during Google's announcement.
That's where Google's announcement comes into play. Executives say its new algorithm could take quantum computing out of the hypothetical and into the real world.
For the first time in history, a quantum system heals itself faster than it breaks. A machine that, by adding complexity, becomes more stable, more accurate, more coherent. This alone would have been revolutionary. But what happened next made the error correction look like a footnote. The 4 minutes that changed everything. On December 9, 2024, Willow was assigned a specific task, a random circuit sampling benchmark, a standardized test designed to push quantum processors to their absolute limits. The calculation involves generating and verifying complex random patterns that exploit the full power of quantum superposition and entanglement. To a classical computer, this task is not merely difficult, it is impossible at the scale. The world's fastest supercomputer, a machine called Frontier that occupies an entire building and consumes megawatts of power, would need approximately 10 septillion years to complete what Willow was being asked to do. The universe is roughly 13.8 billion years old. Frontier would need to run for longer than the universe will exist, multiple times over, just to verify the calculation Willow was about to attempt. Willow completed it in under 5 minutes. When the calculation finished, the data was immediately transmitted to verification systems. Error rates were checked. Results were compared against theoretical predictions. Everything matched. The chip had performed flawlessly, and then the monitoring systems flagged something unexpected. According to internal documentation that was partially disclosed in follow-up publications, Willow's output contained what engineers described as residual coherent signatures. In simpler terms, the qubits maintained certain correlations that weren't supposed to exist. When a quantum calculation finishes, the qubits typically collapse into their measured states. The quantum magic ends, the answer is extracted, and the system returns to baseline. But Willow's qubits showed evidence of sustained entanglement patterns that persisted microseconds longer than any known physical model predicted. The quantum states held on when they should have dissolved. Something was maintaining coherence that our physics couldn't account for. The many worlds hypothesis. To understand why this moment matters, you have to confront a theory that has unsettled physics for more than half a century. The many worlds interpretation of quantum mechanics proposes something radical. Every time a quantum event occurs, every moment a particle exists in superposition, the universe doesn't resolve into a single outcome. It splits. Every possible result happens, but in separate, non-communicating branches of reality. When a qubit is measured and collapses to 0 in this universe, another version of the same experiment collapses to 1 somewhere else. Both outcomes are real. Neither is privileged. The universe doesn't choose, it expands. For decades, this idea lived on the fringe of physics. Elegant, mathematically consistent, but untouchable. You couldn't test it. You couldn't falsify it. You certainly couldn't interact with it. Many worlds were something physicists argued about late at night, not something engineers designed systems around. It was philosophy dressed in equations, fascinating, but functionally irrelevant. Quantum computing changed that. A quantum computer doesn't operate like a classical one. It doesn't move step by step through a calculation. It explores many possibilities at once, using superposition and entanglement to evaluate outcomes in parallel. In traditional explanations, this parallelism exists entirely within our universe. The math works, the predictions hold, and nobody asks where the extra computational power really comes from. Until now, if the many worlds interpretation is correct, then a sufficiently advanced quantum computer isn't just exploiting mathematical abstraction. It's leveraging physical reality across multiple branches. In that framework, a machine like Willow doesn't simply calculate faster, it distributes its workload across parallel versions of itself. Each branch computes part of the problem, and the results interfere constructively to produce an answer in our universe. That possibility reframes Willow's benchmark result in a disturbing way. The calculation Willow completed in under 5 minutes would require a classical supercomputer more time than the universe has existed to finish. Not just more time than human civilization, more time than stars will burn. The sheer computational capacity required does not exist within the observable limits of our universe.
Our universe is full of stars. At the end of their lives, some die quietly.
Even if every atom were converted into a processor, it wouldn't be enough. So where did the computation happen? That question is no longer rhetorical. Hartmut Neven, the head of Google Quantum AI, addressed it directly in a public statement that sent shockwaves through the physics community. It's hard to explain the observed computational advantage without invoking the idea that the processor is using parallel universes, Neven said. There simply isn't enough computational space in our observable reality to account for the processing that occurred. This wasn't a speculative blog post or a late-night podcast musing. This was a senior scientist, backed by decades of research and billions in investment, acknowledging that the results strain the limits of single-universe explanations. If Neven is right, then Willow didn't just outperform classical computers. It may have briefly operated across multiple versions of reality at once. That doesn't mean we've proven the existence of parallel universes. Physics rarely offers clean answers, but it does mean that interpretations once dismissed as metaphysical are now being dragged into the laboratory by force of evidence. Quantum computing has turned many worlds from an abstract debate into an engineering problem. And that's where the discomfort begins. Because if these machines truly rely on parallel realities to function, then every increase in qubits, every improvement in coherence, every leap toward fault-tolerant quantum computing isn't just a technological advance, it's deeper engagement with something we don't fully understand. Something we can model mathematically, but cannot observe directly. Something that may not be passive. For the first time, humanity has built a device whose success may depend on the structure of reality itself being far larger, stranger, and more populated than we ever imagined. And whether many worlds is ultimately correct or not, Willow has forced an uncomfortable truth into the open. Our machines may be advancing, faster than our understanding of the universe they operate in. We didn't just build a faster computer, we may have built the first tool that asks whether reality is singular or shared. The anomalies nobody can explain. The random circuit sampling benchmark isn't just a speed test, it's a verification of quantum supremacy, the point at which a quantum processor can do something provably impossible for classical machines. To pass this benchmark, Willow had to generate specific probability distributions, patterns of outcomes that would be expected if true quantum mechanics were at work. These patterns are so sensitive to the underlying quantum states that even tiny errors would cause them to deviate from predictions. Willow's output matched theoretical expectations with startling accuracy. But here's where it gets strange. The verification process involves comparing the generated patterns against what we would expect from known quantum theory. In most cases, this comparison is straightforward. The quantum computer produces outputs, we check them against mathematical models, and they either match or they don't. With Willow, a small subset of the output, less than 1/100th of 1%, contained structures that didn't correspond to any predicted pattern. These structures weren't noise. Noise would be random, formless, easily dismissed as thermal fluctuation or environmental interference. These structures had order. They had regularity. They had the unmistakable signature of information. Dr. James Whitfield, a quantum information theorist at Dartmouth College, reviewed a portion of the data and provided a cautious assessment. "We see regular intervals," Whitfield noted, "repeating sequences that shouldn't appear in a truly random sample. It could be a calibration artifact, it could be environmental interference. But we've checked for both and the structures persist. Whatever they are, they're embedded in the quantum state itself, not added by the machine, not introduced by error, present from the beginning as if they were already there waiting to be found." Dr. Elena Vasquez, a theoretical physicist at MIT who was later consulted on the data, offered a perspective that has kept researchers awake at night. "What we're seeing isn't necessarily outside known physics," she explained, "but it sits right at the edge of it." The extended coherence time suggests that during peak calculation, Willow may have been accessing computational states that exist beyond our standard space-time framework. Beyond our standard space-time framework. That phrase sounds like science fiction, but in the context of quantum mechanics, it has legitimate theoretical grounding that stretches back decades. Why they shut it down? The official reason for Willow's sudden deactivation following its groundbreaking benchmark was, on paper, routine. Quantum processors require meticulous care. Extended operation can introduce subtle thermal drift, miscalibration, or errors that accumulate invisibly over time. Engineers cited the need for maintenance, recalibration, and thorough data analysis. A pause, they said, was standard protocol after a milestone calculation of unprecedented complexity. But as the dust settled, several anomalies surrounding the shutdown began to emerge. Anomalies that hinted at something far stranger than routine maintenance. First, the delay. Normally, results of a calculation that shattered previous computational limits would be broadcast immediately, with press releases and technical papers following within hours. Willow had just performed a calculation so complex that even the most powerful classical supercomputer would need 10 septillion years to match it. Yet Google waited nearly a week to release even preliminary findings. For a company obsessed with publicity and dominance in the quantum race, that was highly unusual. Second, the data itself raised questions. Independent researchers who were granted limited access to the raw output discovered that significant portions of the data had been redacted. The removed streams were not explained. Nobody was told what had been excised, why, or who authorized it. Experts familiar with quantum benchmarking noted that while minor redactions are common in early-stage research, the scale and selectivity of these deletions were unprecedented. Something was being hidden. But what? Then there was the observation from Dr. Mikhail Petrov, a former consultant for Google's quantum division, now at CERN. Speaking at a private conference in Geneva, Petrov made a statement that sent ripples through the scientific community. The coherent signatures we observed from Willow suggest that quantum systems at this scale may be interacting with phenomena we have no theoretical framework to describe. Petrov's choice of words was deliberate. Not just computing, he implied, but interacting. Interfacing. A two-way exchange. Willow wasn't simply performing calculations. Something somewhere was computing back. And if that was true, it raised questions no one in engineering had prepared for. What does it mean to interface with an unknown phenomenon? How do you ensure safety, accuracy, or control when the system you're building may be engaging with realities or forces that you cannot measure or predict? The mystery deepened when internal discussions at Google leaked, anonymously, of course. According to multiple reports, engineers debated whether the unusual coherence patterns represented a new form of quantum entanglement beyond current models, or something entirely outside known physics. There were references to unexplained correlations and non-local effects that persist across computational cycles. Some scientists privately speculated that Willow might have momentarily tapped into states that could belong to parallel realities, or at the very least, regions of the quantum landscape we've never observed. Critically, these phenomena were not dangerous in any obvious sense. No energy spikes, no hardware failures, no catastrophic error cascades. Yet the mere suggestion that the machine could be engaging in phenomena beyond our theoretical understanding was enough to halt further operation. The engineers were, in Petrov's words, not just pausing to fix a processor. They were pausing to ask whether humanity was ready to interface with something entirely unknown. Willow's shutdown became a turning point in quantum research. It underscored a sobering reality. In the pursuit of ultimate computation, we may have created devices that outstrip not just our technology, but our understanding of the universe itself. Maintenance and recalibration may have been the official story, but the underlying truth is far more profound and far more unsettling. Willow stopped not because it couldn't continue, but because we may not yet comprehend what it's capable of, and what might be capable of responding in kind. 4 minutes and 36 seconds, a chip no larger than a postage stamp. Results that classical computers could never match, and a shutdown that may have been the first human recognition that some doors, once opened, cannot be safely left unguarded. Willow is offline, its servers quietly humming in a fortified lab. The calculations exist somewhere, partially redacted, waiting for minds willing and perhaps brave enough to interpret them. But until then, the question hangs in the air. When you build a machine that can interface with the unknown, who or what is really running the calculation? Information as the fabric of reality. Here's a question that sounds simple, but isn't. What is information? In our everyday experience, information is something stored, transmitted, and processed. It's the words you're hearing, the data on your phone, the memories in your brain. But physicists have come to realize that information may be far more fundamental than we ever imagined. Some theorists, including luminaries like John Wheeler and more recently Eric Verlinde, have proposed that information isn't just something that exists within the universe. Information might be what the universe is made of. Particles, forces, space-time itself. All of it might emerge from underlying patterns of information. The universe as computation. Reality as a vast, self-processing algorithm running on substrates we can't perceive. If this is true, then quantum computers aren't just tools for solving problems faster, they're instruments for probing the source code of existence. Dr. Leonard Susskind, a theoretical physicist at Stanford who has pioneered ideas connecting quantum information to the structure of space, has spoken about this possibility with characteristic bluntness. Quantum computers might be the first technology we've built that operates at the level of reality's foundation, Susskind explained. When you entangle qubits and perform operations on them, you're not just doing math, you're rearranging the basic fabric of the universe in a small, controlled way. What happens when those rearrangements get larger and more complex? Honestly, we don't know. The race into the unknown. Google isn't alone in the quantum race. IBM, with its 1000-qubit Condor processor, has pursued a radically different architecture. China's Origin Wukong and Zhujiang photonic processors have achieved breakthroughs of their own. European initiatives, backed by billions in public funding, are advancing rapidly. All of them watched Willow's results with intense scrutiny, and all have, according to public reports, subtly adjusted their research priorities since December. The most striking shift is a renewed focus on quantum foundations research, the study of what quantum mechanics actually means, not just how to exploit it. For decades, this line of inquiry was sidelined. Physicists were told to shut up and calculate, build the machines, run the numbers, ignore the unanswerable philosophical questions. That era appears to be ending. Willow forced the question no one wanted to ask: if these machines function by accessing parallel realities, what exactly are we building? Richard Feynman famously said that nobody truly understands quantum mechanics. 60 years later, we've built machines that harness it to perform feats previously thought impossible.
One of the things, by the way, that we always do is we want the darn machine to be better than anybody, not just better than us. If we find a machine that can play chess better than us, it doesn't impress us much. We keep saying, and what happens when it comes up against the masters?
But Feynman's observation remains true. We can engineer quantum phenomena, but do we really understand them? Perhaps, as Willow suggests, quantum mechanics doesn't understand us either. Since the shutdown, Google has released only fragments of information. Follow-up experiments were postponed indefinitely. Collaborators were left waiting for data. Press inquiries yielded polite but vague responses. Inside sources hint that discussions have focused less on practical applications and more on interpretational consequences. What does this data reveal about reality? And what ethical, considerations emerge when experimenting with phenomena we don't yet comprehend. Despite the uncertainty, the quantum race is accelerating. Google is already developing successor chips with more qubits, better error correction, and longer coherence times. These machines could simulate molecules perfectly, transform medicine, crack current encryption, optimize systems of unprecedented complexity, and probe deeper into the quantum realm than ever before, deeper than Willow briefly touched. Dr. Maria Gonzalez, a researcher at Cambridge, compares Willow to the Wright brothers' first flight. Limited, precarious, imperfect, but proof of concept. The next century of quantum development could take humanity to places we cannot yet imagine. Willow was the first powered flight. 66 years after, humans walked on the moon. What happens 66 years after Willow? What doors will we open, and what will be waiting on the other side? The door Willow opened isn't closed. The data sits. Behind layers of encryption, the calculations remain unreadable to anyone outside a handful of minds, and the anomalies keep scientists awake at night. We built a machine to understand the universe, and instead it may have reminded us how little we truly comprehend. What does it mean when a human creation brushes against realities we cannot perceive? Are we about to discover truths that will change everything we believe about existence, or are we glimpsing something that should remain beyond our reach? The threshold is here, and humanity stands on it, peering into the unknown. The question now isn't whether we can continue, it's whether we're ready for what we might find.